So today I am doing something I've never done before in the 35 or 40 lectures that we've had, and that's to ask the presenter to return and present not the identical material, but rather expanding on and introducing new material related to our expertise, acoustics. You know, when acoustics in a building are good, we don't think about them. And when they're bad in a building, we're acutely aware and we're pretty critical of them. How is it good acoustics are achieved? Well, we're going to learn today how we deal with that and defeat those challenges. So I'm very pleased today to introduce our presenter, Ms. Rosemary Sue, who is principal consultant at ACENTECH, a multidisciplinary acoustic technology and vibration consulting firm that is one of the oldest and largest organizations of its type. Ms. Sue's creative and integrative design approach has helped guide projects from complex concepts into physical reality. She's worked with architects and owners on numerous award-winning projects, not only to achieve excellent design, but also, important to us here, in sustainability. In her tenure at ACENTECH, Ms. Sue has led acoustic teams on multiple projects involving commercial, residential, and institutional facilities, including this building here, our own ODB. And you might be interested to know that besides our design building here on campus, Ms. Sue and ACENTECH have worked on over 25 projects here on campus. As diverse as the CHP, the central heating plant, in our chapel. So please welcome Ms. Sue.
Thank you so much for the introduction, Carl, and it is a pleasure. I hope you don't mind that I'm taking off my mask for also some visual cues for the Zoom folks that are watching this. So thank you all for inviting me back. I did not know that it's not normal for you to have repeat, but happy to talk about acoustics all day because that's what I do. And I've been doing that for about 20 years. And so a little bit about, what I'm going to go through today is that we just want to understand what it means to work as an acoustical consultant. And also beyond that, I added vibration because that's quite a hot topic in mass timber, and it comes up pretty often. And so as we design more and more mass timber structures, I have some additional insight I would like to share with everyone here. And as Carl said, I'm a principal consultant and I've been at ACENTECH for a long time. We're a national company that is headquartered in Cambridge. And we are hiring. So, if anybody is interested, please do reach out to me. I do have the email at the end of the slide. And our role as consultant, we're kind of in this picture on the yellow part, we're kind of small. And as Carl was saying, kind of silent. And it's probably for the best because usually if there is a feelable vibration or a noise issue, then all of a sudden we're front and center. Or if we're working on a listening space where it has to sound a certain way and it doesn't function as well as we want it to be, then all of a sudden we're front and center. But normally we work along with many of the other specialists under the architects. And so as engineering consultants, that's what we do. So a little intro here about sound and vibration. The first one being that sound is vibration through an elastic medium. It could be through air, through liquid, and it can also through solid. It's a longitudinal movement across. And here's a bigger, so it, in an enclosed tube, it would go back and forth like this. I forgot to put the cap on the other end. A couple of properties that we look at for sound is that first is the amplitude. The amplitude is basically how high or low a level is. So that's the peak of the waves. And if you see over here, Oh, you can't really see my mouse because I'm on the, and then the other thing we worry about is the frequency, is how fast does it cycle through every time it cycles through per second. And so as you talk about it, it's more like similar to having pitches. If you have a higher pitch, it's a higher frequency. If you have a lower pitch, then it's a lower frequency. And other properties include propagation. What direction is it going? How is it reflected? And how is it, intermingled with other parts of the sound? Lastly is speed, and which is that in air, sound is traveling at a different speed as it is in underwater. So if you were designing for something underwater, then we have to account for that. So here's the example I was telling you about, higher frequency versus lower frequency, in a like mathematical way of showing how the waves are. And if you see on the left image that the 1 second you get a lot more cycles, and that's a higher frequency. And the unit is hertz, and lower frequency is on the right image here, which is considered something that's slower and lower cycles per second. Our hearing ranges quite a bit, and every human is a little bit different, even though we try to unify all of us. And so you can kind of see in the image that it goes from 20 hertz on the x-axis all the way up to 20,000 hertz. And the levels are on the y-axis, and the y-axis is reference to a certain pressure level. And as we age, the higher frequency on the right-hand side kind of slowly tapers down. And so we start losing some of our consonances first. And then the vowels are a lot more prominent, and that stays with you unless you have specific hearing conditions. And also here, you can see that we are more sensitive to the mid and high frequencies than the low frequencies. And I just wanted to kind of say, sound is also noise. Like, it's the same definition as an acoustician. However, some people that think of music, to you think it's music, they might think it's a noise. And so I found this XKCD comic that I thought was funny, where they, they're getting the noise from outside and they're trying to cancel from the inside, which really doesn't happen. But, it's a nice interpretation of what to you is music, may be somebody else's noise. And the background sound level that we hear in a space also varies a lot. And that's usually related to the building system and also the environment. So the environment from the outside coming in and how it impacts us on the inside. We're not hearing any traffic here, for example, but if you actually were next to a train track, you would hear a lot of environmental sound, which we would usually use the word noise instead of sound. And in more critical space, then we would start thinking about having it quieter than normal. And so on the left curve here, you see this is a metric that we use called noise criteria. And the lower the levels are, the quieter it should be. And so the NC levels equate to, the quieter spaces. And as we go up the lines, you can see, the words are actually going down, but then the noise is going up on the left side. That there are a lot of spaces where higher noise is actually not unacceptable, whereas some spaces that we need to be very quiet, such as recording studios and concert halls. A lot of strategies are done to control noise related to HVAC systems. And generally, we look at this ahead of time before things are built so that it's not a problem after everyone moves in. And so what we do is we study the HVAC system, MEP system, to make sure that they're quiet. And if they are not quiet enough, we rely on a lot of the equipment information to predict how noisy they might be down a duct. In addition, we collect samples of sound levels in the community and the environment to figure out how noisy a site is. And we can help design the building envelope and make sure that it's actually quiet enough inside for whatever we need. In addition, we think about how the floors and walls and everything are built so that we can think about how we don't hear the wood shop, up in the seminar room upstairs, for example. And those are things we can plan ahead of time so that we don't have as many surprises. Lastly, we try to, for critical listening spaces, we try to make sure that the space is shaped and provided with sufficient sound absorptive treatment so that the space is actually promotes speech clarity, and also for whatever the purpose may be for our use. Vibration is just a different form of waves, right? It is oscillation due to an excitation of a mass. And you probably learned this from physics classes, for those of you that have taken physics. And here you can see it's a single degree of freedom motion. And on the left side is just with a spring, but on the right side, it includes some damping, the constant C. So nothing surprising here. And but in real structures, as you know, it's almost never to single degree of freedom. There's always the fundamental frequency, and then beyond that, there are harmonics to it. And so on the left side, you can see that that's the fundamental frequency, and there's only one level of oscillation. But on the n equals 2, it becomes more complex. And then when you have a rectangular plate, then it has yet another different shape at a higher order. So those are the kind of issues that we want to make sure building structure is addressed ahead of time so that there are as few surprises as we can have. So for vibration, it's in general 100 hertz down all the way to the left. And you can see I made another joke, but it's kind of like the mathematics, and it's all the way at the very end. And it's usually what we as humans or instruments feel in terms of feelable vibration on a building structure. So, usually it doesn't overlap with the sound part, but there is a little bit of overlapping between sound and vibration in the way that we describe a building structure. And the other thing is that there are two main types of vibration transmission, at least on football. The first is that first impact you strike on a floor, and that may be just impulsive sound. But the second type is the more one that's like the joke on the bottom here, which is that when you shake your leg after that initial football, you're actually exciting the floor more, and it may cause floor resonances that transmit down to other things that have the same natural frequency. And so those are actually, this is a good example of what we're trying to predict ahead of time on a floor structure so that we don't have that problem when someone walks down a corridor and you have some very vibration sensitive events happening on the adjacent occupied spaces. And so in the joke here, it's like, well, can you change the rate that you shake your leg so that you don't vibrate my table, but you're vibrating someone else's table? And that is exactly what we're actually trying to do. And so I find that I can relate to that problem. There are also, aside from building structure, there's also kind of like sound, there are vibrations from the environment that we have to worry about. And this is more the case with urban environment where we have subways and trains, and airplane is for sound, but there are ground-borne vibration that may be near your building that we would survey ahead of time and make sure and that it wouldn't be an issue. And actually, not in UMass, but other universities where if you're building a very vibration sensitive science facilities such as fabrication or clean room, then a lot of times we will actually survey the site to make sure that there are no surprises of ground-borne vibration that may contribute to our new building. And a lot of the instruments, in addition to human comfort, which is what we've been describing, and how much you feel vibration from the environment and also from the building, we're actually not the most sensitive. There are other things that are more sensitive, such as the instruments for labs and for vivarium mice are actually more sensitive than us. That shouldn't be a surprise to you, but so if there are vibrations, they may be tolerable of high noise levels, but they may not breed, for example, if they feel too much vibration from an environment or you walking by as near their breeding area. Other additional things that are sensitive to vibration, and some of them also vibration to sound, are imaging equipment. And those are looking at microscopic atomic levels that we have to, imagine if you have something that's imaging a slice of your atom, just to make sure what they're doing, then we want to make sure that image is clear. And if you have a lot of vibration that's impacting the image, some of those image takes longer than a few seconds to collect, then all of a sudden that becomes an issue. So those are the kind of areas that we would worry about vibration. And the critical thing for controlling vibration is we would add stiffness to a structure. And in general, if you imagine if you have columns or beams underneath a plate, then it's going to be stiffer. And then also adding mass, because as you think about it, adding mass means that you'll block sound and you also help reduce the vibration. Other thing is we saw the K is the spring constant and the damping is the C. You can add the damping, and that would also help reduce vibration. For on-grade type conditions, where such as like the subway is coming in, that's a lot more complicated and usually involves isolating the whole building foundation. It's not always effective. And so it's something that's more specialized, but for above grade type structures, that's more easy to predict. So now we're going to go into what that means to our building and beyond for mass timber. And maybe some of you have seen a lot of these resources that the US and also Canada has put out. I'm sure there are many other equivalents in Europe that I can't read or haven't found, but I found the Canadian documents to be probably the most detailed in terms of what to do. And I think the sound and vibration are topics for mass timber, not because we're unique, but also we're kind of the Achilles heel of mass timber in some ways. And then to help kind of promote mass timber, we have to address them. Otherwise, sometimes that becomes the driving issue in mass timber. And so in today's world where we're trying to help reduce embodied carbon, we should think about this, but also keep in mind that the sound and vibration issues do come up occasionally, depending on the type of building we're designing. So for sound and mass timber, the two things we mainly look at are the sound isolation and room acoustics. And sound isolation is how much noise can we block by having mass between the source and the receiver. So that could be your floor, that could be your ceiling, that could be your walls. Room acoustics is more about how the space enclosed is going to sound like with whatever materials we select in that space. So for sound isolation, you're worried, here's an image of a loudspeaker on the left top corner showing how sound might be emitted, and you don't just hear it on one direction, but it's all around you. And also sound travels, as I said, not just through air, but it also travels through structure and fluids. And so you have many, many paths to study when you look at sound. And especially for extremely high level sounds, that such as the wood shop is an example, that those are the kind of items that we look at early on in design. This one, the ratings for the sound isolation then breaks down into two separate ratings that are most commonly used. The left one, it's a little small. The airborne is commonly rated with sound transmission class, which is how much the sound travels through the air, then through the solid medium, and then through the receiver end. Structure borne is kind of what the previous one, all the lines that are flowing through the yellow parts of the structure. And the airborne are more just across the actual element, like the D part, and then the F are all the structure borne. Those are addressed with the IIC rating, which is impact insulation class. And so those two things show up a lot in the mass timber manual as you design buildings. And some buildings are required to meet certain STC and IIC ratings. And so sometimes it drives people in trying to figure out what it takes to meet those numbers, because sometimes they might be too low. So here's an example of that, which is that if you just had bare CLT, you may, the airborne sound through the material is super important, but then you could also improve it by adding mass, and that'll increase the SCC rating. But it doesn't do so much on the impact sound unless we start doing some damping and also what we call an underlayment, so that you can float the mass on top of the wood. And so that helps with the impact sound. And so this is a nice table that kind of tells you a few things to consider so that you can make sure that you get the STC and IIC rating as high as you can. The other thing that I like to do as an engineer, but it's not good for design, is you add a decoupler, which is a suspended ceiling, which is the fourth line down here. But the problem is then it covers up the wood, and then visibly it's not as attractive. So especially in mass timber buildings, we're trying to showcase the mass timber. And so a lot of times we don't want to cover it up kind of like this. So here's an example of when you do suspend a ceiling, and you can see that it helps improve the rating, and the A is just the field condition versus the IIC is the lab condition. So AIIC and AFCCs are field measured assemblies. And this is in case you're wondering, this is a section through the floor, and you can see the suspended ceiling and insulation. So a lot of these manuals and references that are available to all of us have a few preliminary assemblies that you can consider, some of which are also supplemented by vendors that have tested them pretty rigorously, as well as national institutions such as the one in Canada, so that we have all the database to compare and contrast when you're designing a floor assembly, for example, like this one. So now I'm going to talk about more the room acoustic side. So I know the last part was a little heavy because, it's all about sandwiches of floors. But for room acoustics, it's more like about how the finishes impact how sound sounds like in the volume. So when you think about being outside, the sound doesn't really come back to you when you start singing, like in The Sound of Music. It just kind of goes and never returns unless you are singing right at the cliff, and then the cliff reflects the sound back at you as an echo. But when you're indoors, the volume really matters because you're trapping most of the acoustic energy inside and it's bouncing around freely until the energy dissipates or it gets entrapped in whatever material is surrounding the space. So, you know, somebody a long time ago figured out a way to measure how much a certain material may absorb sound. And they used a pipe organ to measure how long a sound takes to decay when you know, measure an impulse sound. And, you know, a body is about the equivalent of 6 of his 6 seat cushions at the time. So I thought that was kind of cool that the man is actually enclosed in the box on the left bottom here, trying to make sure that the absorption from the body is not impacting whatever he was measuring in that room. And this was like an early version of a test chamber. And the metric they use early on, and it's still used in certain variation, is the reverberation time. And so it's just really how long it takes for an impulse sound to decay over time. And it's, like I said, very related to how much volume and absorption is in the room. So longer RT means that, you know, you got greater volume. That seems to make sense, right? Because earlier we saw it's volume divided by absorption. So the higher volume, the greater the RT. And if you have absorption material that are not as absorptive, then you also have longer reverberation time. Or if you don't have enough absorption in terms of square footage, then also you have the problem of having a longer RT. And so when they test these materials, such as the wall panels you see at the back of this lecture hall, actually, what happens is they're measuring how much of that sound energy is coming back or is it getting dissipated within that medium. And once it gets into the material, then it's not reflected back to you, then it's absorbing sound. So when you think about a swimming pool that's all metal and not a lot of absorption, and it's a huge volume, we can end up with a very long RT. And there are solutions and there are materials that we come up with to address that. Oh, what happened? Yeah, so 6 seconds without treatment. But then once we added materials in the metal deck or on the walls, then we were able to, on a project, drop it down to 1.7 seconds, which is quite a bit. And absorption coefficient is just, like I said, a way that we measure how the material behaves. And if 1 is the most absorptive, then 0 is the most reflective. So when you think about brick, wood, actually, concrete, glass, those are all on the lower end. And something like acoustical wall panels is very absorptive. And that's because they have a substrate that helps absorb that sound energy. All right, so switching gear, talking about vibration now. And vibration is a topic that comes up in 3 categories, as I can see, at least from mass timber. One is that when it gets really tall, the wind comes into play because it's having a torsional motion also. That's not what I'm going to talk about today, because there's another consultant that's called a wind consultant, and they study more of this condition, which is quite fascinating. And for us as vibration consultants, we look at a lot, like I said, the above grade condition and also on grade. So for above grade, there are 2 things. There's the footfall from walking on a corridor or anywhere near anything that we're vibration sensitive about. And then there's also structure borne, such as rotating equipment pumps, rooftop equipment vibrating the structure and transmitting that vibration down to a sensitive space. And that can also happen on grade, but also on grade is coupled also with whatever your outside environment might trigger into your building. So those are all the paths of vibration that we worry about. And so let's focus on the above grade one, which is that I think I said earlier, there are three things that the mass, which is what the square we saw earlier in the image of the spring mass system. And then there's the stiffness, what your K constant is on the spring. And then damping, which is the C, which is how much is the structure getting damped. And all of those things help adjust the vibration of a structure. So in one of the mass timber handbook, they have some examples of what the mass is, damping, stiffness. And you can see here that here is what I was saying about the Achilles heel of mass timber, which is that it is definitely not as heavy. So when you think of 5-ply, 7-ply structure, it's very thick. For the same thickness, you can get a lot more with concrete or steel or composite deck. And so that's a little bit of an issue because we're trying to create something maybe where we don't feel the vibration. And the damping is better. So the damping ratio is more comparable to concrete. But material stiffness is another one that becomes a little bit of an area where concrete and steel are definitely much stiffer than mass timber. And then light wood frame, I would say a lot of times those are addressed by having a suspended ceiling, so there's more damping anyways. There's also gypcrete topping we add in a lot of wood frame structures. So for light wood frame, the application is normally used for residential use. And so it's a little bit different and it's a lot more flexible. But for mass timber, because it's competing oftentimes with commercial buildings and also for academic buildings, then we are all of a sudden kind of reviewing all these conditions to make sure that they're actually achieving what we're trying to do for a higher vibration and sound level. So vibration, like I said earlier, there are different things, different spaces have different vibration sensitivities, and human perception is above the red dash line here. And so in general, we're quite tolerable to, like, for daytime, it's 8,000 microinches per second. But for a lot of things that are not humans, it's all below the line, in particular for the research and manufacturing spaces. And so those are, the first question. That this is why it's easy for the light wood frame to be used for housing, and also for mass timber, oftentimes it's used for housing. But once you want to use the mass timber for other uses, we have to ask these questions so that we know what we're designing for it, because it's not one size fits all. And when we measure something at a site, this is just an example from a project of ours where you're trying to figure out whether the vibration is going to transmit to the building structure. And we have to get the raw data first, which is what we're showing here. And there's the red line is the max, and then there's the ambient, which is when nothing, like when there's no train pass by, for example. There is already a little bit of vibration going on at the site, right? And then when you have kind of the train passing by, it peaks, and we try to figure out where the peak might be on the graph so that we can establish what the vibration criteria might be and what it's appropriate for. So to address this, there are a lot of papers about providing more of a composite system. So it's not just pure mass timber, and it has to have concrete, gypcrete, damping. For example, in this building, we added concrete. I don't know like mainly what the main reason was, but there was definitely concerns about sound also. And so we did mass concrete topping over a padding, and it helps reduce increase the mass and provide more damping. And also other ways of increasing the stiffness is by reducing the span of between the beams. So here around campus, you all know this building over here, which is probably one of the first one. It's definitely my first project on mass timber. And actually this reminded me to say that before the DLTs, CLTs, and LTs, there was the mill building. And that was the earlier forms of mass timber that was quite common all around here. And they have a lot of the same issues. Is you want the big, they were used for a lot of manufacturing uses, and they were not usually particularly sound or vibration sensitive. But then when the manufacturing phase went away and they started converting them into offices or housing, then we address a lot of the same issues for sound and vibration, the same way as we do with the mass timber that we see now in this building. And in the student union, I believe that's also some form of mass timber system for the new ballroom, although I haven't personally visited myself yet. And that one, I believe, has steel structure also as a combo, but it doesn't have a lot of places where there was mass timber. It was just like only in the ballroom. Whereas in this building, it was definitely throughout the entire building. And I think that I see the Ulver has a wood columns, but a lot of the buildings today that I've seen more recently have a composite and combines it with steel columns. So, as the design, maybe it's cost driven or performance driven. And I just noticed that more and more it's, with the steel plus the wood on top. And so all of a sudden we start thinking about, well, how much beneficial is that for us, in terms of sustainability, right? Because you're adding back all the concrete and steel that we may want to save. So for the overbuilding, what I was saying about sound isolation and blocking noise, one of the things we had to worry about was, well, if you had a lot of noise coming from downstairs and you have a quieter background space upstairs, what do we do to make the blocking happen more? And additionally, there's also noise going sideways into the common area where you may have presentations also. And so what we did earlier on was trying to figure out a buffer space so that, not this one is a different space, but we try to buffer it a lot of times to avoid expensive constructions so that we don't have to do it everywhere. And in this case, we did that with from this room to the classroom behind, we try to have the storage room so that it's not right next to each other where you have two sensitive spaces. So if you had spaces like this, where it's right up against each other with no buffer space, then all of a sudden, this wall behind us may need to be a much better wall than what it otherwise would be. And this is not a big issue for one or two walls, but sometimes when we work in, there's a lot of repetition and conditions where we're trying to save money so that the building is more efficiently constructed. It's actually really important to plan out those adjacencies and think about them early on in design rather than later. So here's that space. Other things we think about is the HVAC noise and how it impacts the space. And those are all studied early on by having the sound data from the mechanical engineer and the vendors that supply us with this information. And that way we can predict down the duct and calculate how much sound is actually going to get here. And I would say we do this for both interior sound and also exterior sound to the community. And they're pretty, it's not spot on, but there's always some calibration that's needed. But it's pretty good tool for us to figure out these things ahead of time so that there are fewer surprises later on. And then the other thing, as I said earlier, for structure-borne vibration, and that translates to sound also on the higher frequency, is making sure that all the pumps and equipment are vibration isolated so that they reduce the transmission of this energy. And this is literally mass over springs on the solid part you can see in the image here. And that's what we do to try to reduce the sound source and the vibration source. So the left side is a cooling tower, I think, and the right side is just pumps. So this is why when you say, oh, I spent all this money on building a great wall, why can I still hear the noise from adjacent spaces sometimes? It's because vibration isolation may not be addressed, and there's a lot of structure-borne sound, which is usually coming from number 7 down here in the image. There are also other conditions where sometimes to save money or just omission of details, walls don't go up all the way to the structure. Maybe you have really high spec and you want to save the height, and logistically it's really expensive and difficult to build a tall wall. But that also creates a flanking path across, the wall. So it's not always just about the actual mass that's separating the source and the receiver. Oh yeah, so I as I was talking about the wood shop, I just realized I didn't move the slides in the correct order. So to address the noise going to the common area, we added those vestibules instead of adding something more expensive, which is like such as an acoustically rated door, which could be really heavy to operate, very expensive, and wears out over time. So instead, we added a vestibule so that it is a little bit more of a hassle, but it helps reduce the noise going out to the common area. And the glass there was also another concern, and we debated over and over about what type of, how important it is for you all to see the wood shop when you come into the lobby and look at it. And it was a showcase kind of space. And, the BCT lab is not as noisy. And so we didn't think that they have to have the same treatment of glass. And so we kind of debated with the architect while about what type of glazing is appropriate to reduce wood shop activities into the common area. Now, I don't know if that's actually, a noise concern in the end, but, I would say that those are the kind of issues we kind of predict and talk about and try to reduce having these problems. Yeah, so the vestibule is down that way. So it's a lot more indirect, which helps. And we also look at noise from the wood shop vertically to the seminar room and to the chair, it looks like. I don't know if which chair was. And, like I said earlier, we try to make the structure visible so that you can see the wood, but it's not always possible. And so wherever we need a quieter ambient, then we try to either decouple the concrete or we add a ceiling below it, the wood. So you can see that there are 2 options here that were discussed. And that was the window that I was talking about earlier. Sometimes we also add just a separate stud that's separate from the wood structure to help reduce the noise. But in this case, it'll be harder to decouple, because what if you had some other flanking path down the wood or on the concrete? So this is not always the best solution, but it's just another way of addressing when you have a mix of wood plus the concrete plus the drywall. What do you do? on the room absorption side, you know, I said earlier, there's absorption coefficient of different materials, but I find architects often get confused what is blocking, absorbing, and also doing neither. And so, for example, we have glazing with opening. That's definitely not, it's partially blocking sound, but it's not really effective at blocking sound. It's more just plainly for safety, right? For the middle image here, that is used for reducing reflective and reflected energy to the surrounding area. And so that's definitely more for absorption. Does it block anything? No is the answer, because it doesn't have the mass that we need to reduce the sound source to the adjacent spaces. It only helps dissipate the sound energy within the space. And then another common issue that we see is like you spend all this money on a mask to block the sound, and similar to the glazing, if you had a door undercut, then it kind of defeats the point of blocking the sound. So it's very important to coordinate all these details and make sure that everything is executed as finely as it can be. So here's more absorption materials that are in this project. And we have the acoustical ceiling panels here. We have wall panels, and I believe, so the top left corner here, that's also somewhere in this project. And then on the lobby main area, we have the spray type that's on the underside of the structure, which is providing the absorption, because like I said earlier, wood is actually not absorptive. So the wood is down here more as a element that kind of reads like wood, but actually the absorption is high above the structure. So the spray applied is the bottom right corner here. Oh, now I see that. So the wood part is not sound absorptive, and that's very reflective, and it poses a challenge in design that sometimes kind of fights with the aesthetic side. And for us, the wood, the concrete, the drywall, the glass, there was a lot of things that we were kind of struggling to balance with the absorptive element. And you notice that more and more as you go up the floor onto the studios. But the difference is that in the upstairs spaces, I think it's more of a heads down space versus some of your seminar rooms and the lecture rooms where communication is pretty critical across, like this style. So we try to weigh all these things in when we help the architect in deciding what finishes are appropriate. And in the right image here, the problem with that was we were trying to make sure that that is actually used as a presentation space occasionally, but we really wanted to showcase the wood. And so we come to a compromise, which is the first layer of wood ceiling you see is actually not structural like the rest of the building. That's actually an architectural finish. So it's more money. We have to kind of justify that why we want that. Versus the left side, when you see the studios, those are actually the structural wood. And so there's some economy in just using the structural wood as your finished ceiling versus adding yet another layer of ceiling below the structural ceiling that also reads as wood. And we were able to get that because we wanted to spray the structure, and nobody wanted to see the spray that I showed you earlier. Where was that? Yeah, this one on the right side. And it wasn't a dark color. So when you look up, when you walk out, you may see it, but I think that nobody wanted to see that there. Trends have changed actually, and when you go work in offices, there are actually a lot of offices that have them just as the finished product, but when this was designed 6 years ago, it wasn't trendy to do that at the time. So, it's interesting because we have to follow the architects in terms of what's trendy and what's not. And in fact, the ceiling tiles right now are not particularly in trend. And so we actually have discussions with vendors trying to understand why they're not trendy and how can we, sell more acoustical material. And for us, it's also beneficial because we actually want more absorption in that space. So, in the student ballroom center, that was also a little bit of a challenge because they wanted the wood exposed. And what do we do in ballrooms? We have weddings, we have lectures, we have loud events and dance events. And as a compromise, they added a lot of wall panels, and they have these in the image here. It's kind of hard to see, but the red baffles that are in between the trusses. And that was the compromise we came about, which, it helps provide absorption. But whenever they have a really loud event, I would imagine sometimes the noise built up is quite loud in there. Another extra thing that only a few companies that make the laminated timber do is actually adding the absorption in the structural element. And that's the DLT, the Dow laminated timber, versus your more traditional trough laminated timber that are horizontal. And the problem with this is DLT has a different structural strength than CLT, but the benefit is you can have 2-in-1 for acoustics, which is you have the absorption and you have the structural part of it. So unfortunately, the way that a lot of public jobs are, it's very hard to find 3 equals. And so DLT, I have not seen it a lot in projects around Massachusetts at least, but we try to discuss this earlier on so that the structural engineer can have a buy-in if this is actually something that we can go towards. And so even though we told them use DLT, CLT, I believe, was the selected one over the DLT as their final choice. And being a state school, they have to have 3 equal, and we couldn't find 3 equals. So that's why they added the absorption like the way they did with the hanging baffles. And for the, like I said, with the negotiation with the design team, a lot of times we struggle with the form versus the function. And sometimes we want the aesthetics to kind of trump the function. And so for example, in the studio spaces, that you will notice that there is not as much sound absorptive finishes as we would like, but it is gorgeous and the daylight is amazing because you got these giant windows up to the deck. So, we understand, because when we have these discussions with everyone, they're like, well, I want it a certain way because I want the windows to be maximized, so I don't want to drop ceiling. And then there's another, consultant that's like, well, I also want this. And so everyone is trying to kind of pitch what's important to them. And so for us, it's like we have to balance that all out with everybody else in the design team. And I would say that, for us, it's hard because then you have spaces that are too reverberant, and occasionally it may be, really hard for people to work in those spaces. And so I use the top floor studio, is it the landscape department still, as an example, because they also have the PhD students overlooking the area, and then they have a greater volume than the lower floor space studios, and you really notice the longer reverberation time. So in case you're curious, you should go upstairs and kind of listen to it yourself and experience that. Another type of project that I recently, our firm has worked on is the Penn State, one of their College of Engineering building, which is actually very similar to the BCT department from the way I read it. It's actually not science laboratory building. So their vibration criteria wasn't as stringent as I would imagine, but it is used for building engineering testing. And they have a lot of maker fabrication labs. And so they're allowed to have higher spans between and with fewer columns and such. And so the stiffness of it is not as critical. However, for sound, they do care about it. And so there is concrete topping on top of their 5-ply CLT. And in housing, mass timber is also used quite commonly actually around the country. And you can see over here, this is a project in RISD where they left the structure exposed so that you can see the underside of the CLT, and they added the drywall as the walls. And but they ended up having to help improve the sound isolation of the assembly. They added gypcrete on top of the padding, so it helps provide a decoupling, but they added a little bit of mass, but it's not as substantial as adding concrete. So there are ways definitely to kind of have a balance, and they're generally trending towards a composite structure rather than just like a straight up, wood structure. So as we work on more of these types of projects, I do see that, there is a little bit about, and you can see I don't know if all the columns are concrete, but they have a concrete column on this image on the left and not the wood columns like we have. Lastly, I'm just going to go quickly. There are a lot of tools we use to predict sound and vibration. And we do use SketchUp also to prepare the shape of the space a lot of times and import it into our own applications and different programs to analyze acoustics. So for room acoustics, that's what we definitely use. So I believe that you all are familiar with SketchUp. And then we import it into our own modeling software that is more used in the acoustician world. And that's how we can predict how sound propagates in an enclosed space. And similarly, we use that for speech amplification and sound reinforcement system and the geometry, because it's very difficult to just import Architects or Revit model. Revit is probably the most commonly used. However, they often are not enclosed. And so in sound and lighting actually modeling, we have to recreate the model from scratch with SketchUp and make sure all the planes snap and that no sound and light is leaking out of the space. And so, these are another example of that. For vibration, I think we don't use SketchUp. However, we do kind of rely on PDF and measuring those out, and then using our MATLAB scripts to calculate how footfall behaves in the structure at different walking speeds and checking for the resonance that are created. And so there are many tools that I'm sure we can use to help predict our sound and vibrations that we are still exploring, but these are just a few examples of them. So that's all I have today. And thank you very much for listening. And hopefully you found this informational, and that if you have any questions, please email me or ask me right now. Thank you.
Yeah, you mentioned the mills earlier.
Yeah.
What's your go-to solution for upgrading acoustics in mills?
Yes, mill building is usually the problem is structurally they can't handle more mass, and so a lot of times we ask for something lighter, such as gypsum concrete instead. And a lot of times we decouple the gypcrete from the base structure of the wood, and also we try to suspend the ceiling if they allow us to. And of course, with mill buildings, just like mass timber, everyone's trying to showcase the beautiful mill underside. And so there's only so much we can do, at least for residential side, to meet the code. But for commercial use, like offices, there are plenty of offices that don't need to be as quiet because you can, if you hear a little bit of sound from upstairs, it's not as intrusive as housing. And so depending on the use, we've definitely done that. And there's also in the past, we, not me, but the architect did the faux wood on the underside, but then that kind of defeats the point of, you do a reclaimed wood underneath the real thing, then it's like not as sustainable. So
About the loads, because mills usually have industrial loads. And
Exactly.
They reduce that to a residential load.
yeah, exactly. Yeah. Exactly. I agree with you, but I don't think all mill buildings were used for like the same load, right? If you were doing heavy industry on grade, but then up higher they were doing like machining, and the machine is much smaller, like sewing, for example. And all of a sudden, that's not actually accepting the load. Either that or the structural engineers are all very scared and they're just very conservative, and then they tell us, no, you cannot add any more mass weight to it. And so we trust that they have, that they kind of control the situation for us and drives the bus. Yeah. But I think that I would imagine that they could also add steel to the bottom to help structurally support it. And I don't know if that's been done. I would imagine so, depending on the type of building that it used to be. You have a question? Yeah, there's a whole subset of field for construction noise and vibration, and there are tools that we have developed that's more of a real-time. It's more about so the answer to your question is there's nothing one can really do to eliminate the vibration intrusion to whatever you're experiencing, but there's a way to reduce the amount of it or the frequency. And so for us, we develop a communication tool between the people generating the noise and the vibration and the receivers. And oftentimes they're like the professors doing the research near this construction site. And so they have more real time. If somebody's like jackhammering right there and they're like, I am actually trying to do an imaging right next to you. Can you, do it at another time? It helps the communication. It's amazing because that we have a way of both sides can see if the source is actually coming from the construction team or not, because there are multiple like plots that show the remote monitoring of what the vibration is generated, because it's not always generated from what you think it's coming from, and they have to go kind of find where the source of the vibration might be coming from in the construction zone. Yeah, there are material. Yes, the question is whether in swimming pools the spray is what is used in the at the material, and so I will say that the pool is a really challenging one because honestly the materials degrade over time really fast. I think it's the chlorine also that causes the condition, but there's always the structural deck that's actually has the absorption in it. But when that's not added initially, then all of a sudden you do have to tack on the absorptive material to the underside of the deck, such as spray. And then the other problem with pool is if you actually suspended absorption underneath the structure, they actually need the air ventilation so that it moves around so that there's no mold growth developing. So it's another, it's like I almost rather the pool be reverberant than having mold. And so it's definitely another balance that we fight, kind of go back and forth with the designer. Yeah. So in the design, the what is it, the hygienist that they trump like the pool consultant tells us like you can and cannot do these materials, but a lot of the vendors will tell you we can put this in the pool, and then we have to kind of hash it out to figure out if it actually is the case. And that happens also in a lot of science labs where things can grow in material or ductwork, right? Can you have lining in a ductwork or not? And does that create microbial collection over time? And And as long as there's moving air, usually that the answer is yes, you can have those things. But once you stop having moving air, that's when those things happen and mold grows. Thank you so much.
Thank you on Zoom.